Hi everyone, in today's video we will make an attempt to prove a rather generic result or an abstract result related to the convergence of perceptron learning algorithm when the data is linearly separable. In the previous video we saw the example of the OR gate where the classes were linearly separable. AND gate is another example of dataset with linearly separable class. We claim that the perceptron learning algorithm will converge in a finite number of steps in case we have a dataset which is linearly separable. We will consider the feature matrix X over here as we did before, but we will assume that we have n features. So these are the n features. The value of n was equivalent to 2 when we talked about the OR gate, which meant that we just had x1 and x2 and the entire column x1 and x2 were present. But we will consider more than two features in this derivation to generalize the result. We will further assume that the number of observations considered is finite, which is m. The value of m was equal to 4 when we were talking about the OR gate. But again, to generalize the result, we consider the value of m, which is greater than 1. We can write the X matrix, which can also look like this. So this is the X matrix. Each and every observation over here could form a vector like x1. We can write it as x2 and so on till xm. So if I consider this term xm, it will consist of the entire row vector which I am highlighting over here. Corresponding to each of the m observations, we have the target values yi as shown over here. These are the target values. Each of the yi could be either -1 or +1. The yi could belong to -1 or +1. Exactly in the same way as we proved in the previous example, which was related to the OR gate, uh, because we are solving a binary classification problem. Like before, we need to determine the value of this vector w, which consists of w1, w2, and so on till wn, corresponding to each of the n features we have considered in the feature matrix and the bias term b. So we will now assume w star, which will be the set of optimal weights, that is the weights we aim to reach such that this condition holds. This means that all the classifications done are correct with the weights in W star. If we recall from our previous video, we know that this term yi xi w star is positive when the classification is correct and negative when the classification is wrong. So this is exactly the slide I was talking about, or the part I was talking about from the previous video, where we were trying to prove that whenever the classification has been done properly, the term wi xi w star is positive or w is positive, and whenever an incorrect classification is done, yi xi w will be less than 0. We further assume that w star has a unit norm. We proceed a step further and try to estimate gamma, which is the margin of the hyperplane, defined as this. Now, let's try to understand what this term gamma and the hyperplane means. Let's say we have the equation of hyperplane, and it is separating two set of classes. Let's say these are the positive classes, and we have the negative classes over here. Um, so this value of gamma is the least distance between the closest point from the hyperplane. So it takes into account the distance from all the points in the hyperplane, like it took the distance from this hyperplane till here, perpendicular distance we mean. It took the perpendicular distance over here. It took the perpendicular distance over here as well. And amongst all the perpendicular distance available, it considered the point or the distance which is shortest from the closest point from the hyperplane. Now to find that, we already have defined the matrix X as this. So this is how the matrix X was defined. We already know W star So we will multiply x with w star, and each of the rows which come out of it, it will be x1 w star, x2 w star. We will try to find out the minimum value out of it. So this is going to be a scalar constant only, because x1 will be of dimension 1 cross n plus 1, because we have n features and one term is for bias, and w star is of order n plus 1 cross 1. So from our first video, we did find out the gradient ascent update rule. This was the gradient of f, if you remember. We assume that for any step k of our iteration, we are not able to reach w star. We see some misclassifications which will be pointed out by the fact that this term will be less than 0 according to the rule which we have set up previously, and hence we will have to perform an update of wk to determine wk plus 1. This is the updated weight which we have, and with every upgradation or every updation of the weight, we will try to find out how closely we are to w star. So we find the projection of wk plus 1 on w star. For that, we plug in the values of wk alpha x transpose y over here in place of wk plus 1, and multiply it with w star. So this transpose goes inside and we get wk transpose. Alpha is a scalar, the transpose is having no effect on alpha. X transpose y becomes y transpose x, and on multiplication we get a value like this. So we will solve this further, but we will try to find out what this xw star exactly looks like. So this is how xw star is defined. We now use the definition of margin which we defined previously. So if I just scroll up and see the definition of margin, margin was the minimum value of each of the corresponding dot products of the observations with w star. And what exactly we have over here is the fact that we have these observations x1 till xm, and we are doing a dot product with w star. So this is the individual observations which we have, and it is lower bounded by gamma depending on the definition which we have just defined. On solving further, we get this as a result. Now we will pre-multiply with y transpose and get the following result. Uh, since y transpose is again a vector, this is a vector of ones, and on multiplying we eventually get a scalar which is summation of yi's, and gamma will stay as it is. It's going to be a scalar anyways. And we now multiply both the term with alpha. Alpha is greater than 0, and multiplying both the terms with alpha will have no effect on the inequation which we have derived over here. Now we eventually add yk transpose w star on both sides, because this is again a quantity which is going to be positive with no effect on the inequation. And since we know that wk transpose w star plus alpha y transpose w star, or this term, is exactly what wk plus 1 transpose w star was, we just impute it and get the following relationship. This is the relationship which we have attained over here. We see that we have obtained a recurrence relationship over here. Now we are going to substitute for different values of k from 0 to m, m being a finite value which could be the number of iterations which we are trying to prove is finite, or it is bounded by some value. So we will start with 0. When we plug the value of 0, we get w1 transpose w star. This term is a constant, it will stay as it is, and this will be w0 transpose w star as it is shown over here. And then we proceed further. We say that since this is a constant, we make this assumption that this is equivalent to c, and then we put the value of k as equal to 1. We get w transpose w star greater than equal to this term c will remain as it is. since we have imputed the value of k as 1, we get W1 transpose W star. And now if we proceed a bit further, this is what we can get. So this is W1 transpose W star. From a step before, it was greater than C plus W not transpose W star. We just impute it over here and we see that W2 transpose W star is greater than twice of C plus this term. Now we proceed further with W3 transpose W star, and then we are able to find out that it's greater than this. Now if we keep on doing it recursively, this is what we are going to get at the mth stage. So since Wm transpose W star is greater than this term combined, um, and whole is always greater than a part, that's what we can use over here. We can definitely say that Wm transpose W star will be greater than equal to Mc. We substitute back the value of C which we defined here, and we get this as one of the relationships. Like we started with the assumption that W star is the point where we needed to reach, and we were able to get a recurrence relationship and eventually got a relationship which is lower bounded by some value. So we have assumed previously that W star transpose W star is equal to 1, or the norm of W star is 1, because this was one of our initial assumptions. We will like to see that after performing k plus 1 iterations, what Wk plus 1 transpose Wk plus 1 will look like. So this is exactly what we get on performing Wk plus 1 transpose Wk. So this is the gradient ascent upgradation of Wk which we have established, and we will put this transpose inside, or we will use the transpose on each of the individual terms and multiply the terms individually to get this as a result. There are few things to note over here. I am able to combine these two terms into one. I have combined both the terms into one. This is because of the fact that both the terms are scalar. So the dimension of Wk is n plus 1. So Wk is of order n plus 1 cross 1. X is of order m cross n plus 1. And likewise, y is of order m cross 1. Now if I follow this Wk transpose will be of order 1 cross n plus 1. We multiply with x transpose which will be of order n plus 1 cross m, and eventually if we multiply with y which is of order m cross 1, we get a 1 cross 1 matrix, which will mean that this is actually a scalar. The same holds for this result as well. Now if I do y transpose, it is 1 cross m, x is m cross n plus 1, and if I consider Wk is of order n plus 1 cross 1, and on combining the multiplications of y transpose x and Wk, we are going to get a scalar of order 1 cross 1. So we are able to write it in this way. We are further able to write this term as well. This is again a scalar. It will follow the same route, like y transpose is 1 cross m, x is going to be m cross n plus 1, same x transpose is n plus 1 cross m, and eventually y is of order m cross 1. So we get two scalars over here in our calculation, and this is a dot product. Now and anyhow, the dot product between two vectors which we are considering is going to be a scalar only. Now the entire task which we have to do is to resolve these two terms, the highlighted terms, in a way so that we get an inequality. So we first consider the twice of alpha y transpose x Wk term. This term I am considering. So we know that y transpose x W star is maximum. So this is established very much in the previous video which we did. Like we had the objective function fw to maximize, y transpose xw we wanted to maximize, and since W star is one of the solutions which is giving a zero misclassification, which will mean that in this derivation as well, y transpose x W star is the maximum value which we can attain. And for any Wk which is less than, so for any Wk which is not W star, this inequality will hold. Because there are going to be some misclassifications in Wk. That's why we proceeded to calculate Wk plus 1, and W star is giving us perfect results. So in any case, we are not going to get perfect results out of it. It's always going to be less than this term. Now, this entire term we assume as K1, and we bound this particular term with twice of alpha K1. This is going to be the upper bound of the term 2 alpha y transpose xwk. We proceed further, and what we observe is, as I have explained previously as well, this term y transpose x into x transpose y is actually a constant. So we just assume it to be K2. Over here, there is no such involvement of any of the weights, so there is actually no need to bound this term or use any sort of inequality in this term. So what we can say is this is just a constant term because this is a scalar term which we have obtained. So on combining this inequality and this assumption along with the recurrence relationship which we had for Wk plus 1 defined over here, we eventually get an inequality which looks like this. So Wk plus 1 transpose Wk plus 1 will be less than this 2 alpha k1 plus alpha square k2, and we add this term on top of it. We will now recursively solve for all the values of k, 0, 1 till m. On doing so, we first put the value of k to be equal to 0. We get something like W1 transpose W1. This is a value of 0 attained over here. That's why we get W0 transpose W0. Since both these terms are constant, we can combine both of them together with the value of k. And we proceed further with the value of k is equal to 1. We get W2 transpose W1, which is less than W1 transpose W1 plus k. We use the same inequality we used a step before to express it in the term of W0 transpose W0 plus 2k. We can proceed further and eventually end up with this inequation. Now there is one thing to note over here. W0 transpose W0 is going to be a positive number. So if W0 transpose W0 is positive, and if m is the number of iterations for which we need to run the algorithm, we can multiply it with m and get this as a result, and that forms the basis for our final inequation which is determined over here. So we have got two inequalities over here. So this is the first inequality we got by considering the projection of Wk plus 1 on W star. And this is the second inequality we got while we were trying to find the projection of Wk plus 1 on itself. We will consider now the first inequation and use the definition of dot product. So this is how the dot product is defined. So A dot B is equal to norm of A into norm of B into cos theta. We will now use the assumption that this norm of W star was 1, and the fact that cos theta is always between 0 and 1. So if we consider this term, it resolves to norm of Wm transpose cos theta. And since cos theta is less than 1 and greater than 0, this will mean that this entire term will be less than equal to Wm transpose. This is what we were able to find out over here. We will now proceed a step further to write it in the form of the inequation which we have obtained. So this Wm transpose W star from the first equation is lower bounded by this term and upper bounded by Wm transpose norm. So we combine both the inequations to obtain this relationship. So we are going to write Wm transpose in this form. Since we don't have a square over here, we have to put a square root. And from here, we can clearly observe that Wm transpose Wm could be solved further by leveraging this inequality. But this term is in form of a square root. So what we will do in the next step is to square both sides. Since both the terms on both the sides of inequality are positive, squaring them won't have any effect on the inequality. So now we proceed further to use the inequality number 2 over here, and we get a result like this. So if we see carefully, we have a term m over here, we have a term m square over here. We can cancel 1m out from both the LHS and RHS. And on even proceeding further, we get this as a relationship. Now, if we solve it, what we are observing is m is less than equal to this. So this is the upper bound of m. So this is what we wanted. So let's understand carefully what it means. The number of iterations to converge, in our case the value of m, is dependent on initial weights. This is the initial weights, W naught transpose W naught. Uh, and if you have seen the previous video where we were solving the OR gate, you have seen that corresponding to different values of our initial weights, we were getting different results. And likewise, we were getting different results corresponding to different values of alpha, which is the learning rate. It also depends on the value of gamma, and which is the margin of separating hyperplane, the sum of squares of target values, and the maximum value of gradient, like x transpose y was the value of gradient we established in the first lecture, and is the maximum value of the function. Like we were able to say that we have a function fw which was equivalent to y transpose xw. The maximum value is attained when we have w replaced with w star. This is the maximum value, and we have the gradient of f as equivalent to x transpose y, which we proved that time. And this term is ideally gradient of f transpose gradient of f. So the square of gradient, kind of. So we see that under a given set of conditions, the convergence is guaranteed in a limited number of iterations when the data is linearly separable. We did the entire proof based on batch updation of weights. The proof was centered around the idea that if we have a significantly large data, we divide the data into smaller chunks called batches, and we upgrade our weights after processing one batch of observations. However, in most of the literature I explored while making this video, I found out that the update is mentioned in a stochastic way. This means that the weights are updated after the misclassification of each observation. I will point you to a link where the stochastic updation of weights is explained in a nice and understandable way. So I followed this site and I followed this lecture, and if I scroll down a bit below, it does the exact same thing which we did in our video. These are the linearly separable data points which they had, and they proceeded with the perceptron algorithm where things are happening in a stochastic way. So for each of the observations, they are performing a gradient upgrade rule. So this is the gradient upgrade rule which I am talking about. And on proceeding further, they have made a proof of the perceptron convergence theorem in the exact same way as we did, with a little bit more assumptions and relaxations to conclude the exact same result, that the number of updates needed by m is bounded, or the m converges in a finite number of steps. I will link this lecture in the video description as well. So that's it for today. Thanks for your time.